today I'm gonna show you a little lemma about modular inversion. You might already know it, it's not that hard, and also you might assume it intuitively. So let me maybe first give you an example. So let's look at the integers. Let's say a equal to 4, b equal to 2, and now we wanna know what a times b inverse modulo 5 is. So, well, b inverse, not b to the minus 2. So, let's see. So, a is 4, b is 2, so the inverse of 2 is 3 modulo 5, so that's 12, which is 2. And also, now let's look at this thing over the rationals, so a divided by b, so this as an element in the rationals, well, this is also 2. And that's no coincidence, so maybe you wouldn't even bother thinking about it, but here we have division in the rationals, and here we have inverses modulo 5, so now we want to prove that this holds in more generality. So let's see, let's state it as a lemma. So let R be an integral domain, and we assume that A and B are elements in R, I in R is an ideal, and B is invertible in R modulo I. So also note that here, because we took 5, so our ideals would be just the ideal generated by 5, and then we would have the integers modulo 5, that's a field, so of course 2 is invertible, and we already also know the inverse, namely 3. Okay, so that's the setting, and the claim is that A divided by B as an element, we have one further assumption. So we assume that A divided by B is in the ring. So this is at first an element in the quotient, in the field of fractions, and then we assume that it's actually in the ring, and then we have that A divided by B is congruent to A times B inverse modulo I. So that's the statement. So let's see in our example. So A divided by B is also in the integers. So we have that, and well, that's exactly the setting. And well, actually we want B to be non-zero, but we have this immediately because it's invertible in this ring. At least if this is one could argue what would be the case if I is actually equal to R. But so let's say I is not R. Okay, so let's prove it, and the proof is quite easy. So A divided by B is some X in R. Now let's look at this equation. So that means that A is B times X. In also this equation holds in R. And so we get also that A is Bx modulo I. And so we get that A times B inverse is X modulo I, but X is A divided by B. So that's already the proof. So it's very short, and yeah, but the thing is, it can come in quite handy, because normally we would calculate inverses by the extended Euclidean algorithm, or we could just try and see if we can guess them. But in this case, we don't have to, we just use division in the ring. So if we have, so for instance, in the integers, we just divide 4 by 2, and we get that we have 2. And you might wonder if this has any applications, and indeed it has. For instance, you can look up the Montgomery multiplication algorithm. So that can be used, for instance, for square and multiply in the setting of RSA or other settings. So that's one application where one can use this lemma. Okay, so that's it for this video. I hope that was clear. So the proof is very short, and yeah, I hope to see you next time. Maybe I'll do a little bit about Artinian rings, but well, we'll see. So see you, bye.